Hi everyone, welcome to the General Maths 3 and 4 lecture. My name is Manjot Bulla and I'll be taking your lecture today. So just before we begin, I'd like to talk to everyone about ATAR Notes. So ATAR Notes is a really amazing company. They provide a lot of free resources to many students around Australia. So if you go to their websites, atarnotes.com, you can find a lot of study notes, lectures such as the one that you're watching right now, discussions, a lot of engaging online revision videos, newsletters, ATAR calculator, a lot of articles that provide study tips and strategies, and heaps more. So it's a really valuable resource that's worth checking out. They also offer TuteSmart, which is online tutoring for students, as well as study guides that are printed revision materials, and they contain a lot of really good tips and a lot of study notes that can help you prepare for your individual subjects. And they also have Ed Unlimited. So Ed Unlimited is just a bank of all these study guides and other resources from both NEEP and ATAR Notes. It's sort of like a subscription service, so you get access to all these resources, which is amazing. So really worth checking out their website if you want more information. Okay, so now I'll introduce myself. So my name is Manjot Bulla and I graduated last year with an ATAR of 99.80 and a 50 study score in further maths. And I'm currently studying the Bachelor of Biomedical Science at Monash. And I'm also a general maths tutor at TuteSmart. And the subjects that I did throughout VCE were chemistry, maths methods, specialist maths, English, biology, and further maths, of course. Okay, so today we'll be covering basically matrices and networks. However, there will be no designated break, so pause whenever you need, or if you're watching the live lecture, you can also use the Q&A software to ask questions, and I'll be monitoring the chat, so I'll be reading the questions as they come up. Okay, so let's get started with the first topic. So firstly, we'll be going through matrices. So I have included the key knowledge dot points from the VCAR study design, but mainly we will be covering matrix arithmetic. We'll be looking at the inverse of matrices and how to find the determinant, and also the conditions for when a matrix may have a inverse. We'll be looking at the different types of matrices and how we use them throughout this topic. We'll also be using how matrices are used to represent information. We'll be looking at binary and permutation matrices as well as their properties and applications. We'll be looking at communication and dominance matrices and how we analyze those and do calculations. We'll also be looking at transition matrices and using recurrence relationships to sort of predict the future using matrices. And also the new addition to the study design, we'll also be looking at Leslie matrices and how we interpret those. We'll also be looking at the steady or the equilibrium state of a matrix, and we'll also be using transition diagrams to sort of convert them into transition matrices and then use those to do calculations. Okay, so let's get started with matrices. So matrices are essentially just another way of representing information. And that's what we're going to sort of really look at throughout the whole lecture. So when we move on to networks, you'll see that networks are also another way of just representing information. So matrices are usually just rectangular and they're usually presented, or they usually contain these square brackets with elements inside. So the individual entries in the matrix are called elements. And these elements don't always have to be numbers. They can also be letters such as this, or they can also be symbols such as pi. And a matrix is usually arranged in the form of rows and columns. So we'll get to that. So a thing that students often mix up is columns and rows in a matrix. So rows are the horizontal sort of arrangements in the matrix, whereas the columns are the vertical sort of elements. So they go up, down for columns, and rows go horizontally, so they go across. So it's really important to know this when we get to matrix arithmetic. Okay, so because in a matrix we can have a lot of different elements, there needs to be a way to sort of denote the position of certain elements. So for example, if we have a really large matrix and we want to refer to a specific element, because like I said, matrices are just another way of representing information. And if we want to sort of identify certain elements in the matrices, we have a way of sort of denoting the position of an element. So we use a method of denoting their row and column to sort of identify their location. So for example, if I wanted to, for example, determine what this element was, or I wanted to point out what this element was, the way that I would sort of denote this element would be A, so the name of the matrix. So the name of the matrix is A, and then the row, so this element is in row 2, so row 1, row 2, so this element is in row 2, and column 2, so row 2, column 2. So therefore, this element would be A, the row number, which is 2, and the column number, which is 2. So this element 8 would be A22. So this is how we sort of denote specific elements in the matrix. So if we were to identify what this element was, so 25, so we use the name of the matrix, which is A, and then the row number, so the row number is row 1, and then the column number, so the column number is 2. Sometimes the rows number and the column number will be separated by a comma, but that's not always going to be the case. Sometimes they'll just written as 1, 2, and this is equal to 25. Okay. Okay, so another thing that we can use to represent a matrix or to sort of identify a matrix is the order of the matrix. And the order of a matrix is again just a representation of the size of a matrix. And it's usually found by this formula over here. Well, it's not really a formula, but it's the number of rows times the number of columns. So it's not actually a formula. So we don't actually find the number of rows and then we multiply that by the number of columns. This is just the notation. So for example, in this matrix over here, so it's the exact same matrix, if we were asked to find the order of this matrix, all we would need to do is write down the number of rows. So this contains 1, 2 rows, and then multiply that, or well, not multiply that, but it's just a symbol that we use, by the number of columns. So 2 by 2 is the order of this matrix. So the answer is not going to be 4. It's just that we write it in the form 2 times 2 or 2 by 2. And this is just a representation of the size of the matrix. Because if we were to have a really large matrix, that would have a really high order or a really high number of rows and columns. Okay, so here are the different types of matrices that you will encounter throughout VCE. So some of them are important, whereas some of them are not that important. You probably won't see them often. We'll be going through each of these different types of matrices, or most of them, as we go throughout today's lecture. But the important ones are square matrices. So square matrices are essentially having the same number of rows as columns. So a square matrix is essentially a matrix that has the same number of rows as columns. So this one, for example, is 4 by 4 if we were to write its order. and that would be the square matrix. So 3 by 3, 2 by 2, 5 by 5 are all square matrices. Column matrices only have one column, so they can have as many rows as they want, but the number of columns is always going to be 1. So for example, the order of this matrix would be 3 by 1. So only one column. Similarly, a row matrix contains only one row. So it can have as many columns, but it will only contain one row. So the order of this matrix would be 1 by 3. We also have rectangle matrices, so you won't really see these matrices quite often. But the important thing to note from this slide is really having a page in your summary book where you have an example of all of these different types of matrices written down, because most of the time in the exam, they will probably ask you, give an example of a permutation matrices in the probably exam 1, the multiple choice exam. They'll say, they'll give you like this matrices and they'll say, this is an example of what different types of matrices, or what is it not an example of? And they might give you the options, for example, a permutation matrix, square matrix. So that's the sort of questions that you're going to be getting. So they won't specifically be like, what is this matrix? It'll usually be in the form of giving you a matrix and then asking you to identify what different types of labels it might be associated with. So for example, this matrix is a permutation matrix, but it's also a square matrix. And it's also a binary matrix. So we'll have a look at those. So for example, this matrix, a rectangle matrix, well, it's not a square matrix and it looks like a rectangle, so it might have more rows than columns, or it might have more columns than rows. So this one has 3 rows and 2 columns. So therefore, the order of this matrix is 3 by 2. Okay, and then we move on to binary matrices. So binary matrices only contain 1s and 0s. And that's just the rule for a binary matrix. So for example, this matrix is also a square matrix whilst being also a binary matrix. So this is what I was talking about. A particular matrix can have multiple labels. But a binary matrix only contains 0s and 1s. Then we have a diagonal matrix. So a diagonal matrix only has numbers in the leading diagonal. So this is the leading diagonal, and it will only have numbers in this leading diagonal. All the other numbers are going to be 0. So that's the rule for a diagonal matrix. And it's also going to be a square matrix as well. So that's another example of a matrix that can have multiple labels. For example, this one is 3 by 3. So a diagonal matrix, just to recap, is a square matrix that only contains elements other than 0 in the leading diagonal. So the leading diagonal is starting from the top left going all the way to the bottom right, regardless of how many rows or columns it may have. And it also needs to be a square matrix. Then we have a 0 matrix, pretty straightforward, it only contains 0s. Then we have an identity matrix. So this matrix is really important when we get into matrix inverses. So an identity matrix is essentially a type of diagonal matrix almost, but it only contains 1s in the leading diagonal and all other numbers are 0s. And it is also a square matrix as well. So 3 different labels. So diagonal matrix, a square matrix, and obviously an identity matrix. So it only contains 1s in the leading diagonal and 0s as the rest of the elements. So this is 4 by 4. A symmetrical matrix. So we'll get to transposing matrices later. It will make more sense, but essentially, if you were to flip the rows and the columns, they would be the exact same. But we'll get to transposing matrices next, in the next slide. So we'll have a look at that. And then we have permutation matrices. So permutation matrices are essentially a type of binary matrix almost, but they only have one in each row and each column. And it also needs to be a square matrix as well. So same number of rows as columns. So permutation matrices are also really sort of common matrix type that you will see. Sorry, this is 3 by 3. as we go through the lecture today. So this is a 3 by 3. And then we have the upper triangle and a lower triangular matrix. So these are pretty straightforward. So for an upper triangular matrix, it will only have elements in the upper half, or should I say numbers. Okay, so we have the leading diagonal. So it's sort of like a diagonal matrix. So it has numbers in the leading diagonal. So in an upper triangular matrix, there will also be numbers in the upper triangle. So all numbers sort of above the leading diagonal, and zeros for the lower part. For a lower diagonal triangular matrix, you will have numbers below the leading diagonal and also numbers in the leading diagonal, and only zeros above the so when I mean above, I mean like if you were to look at the diagonal and then you will only look at the numbers above the diagonal. So a little bit strange. You won't so these are really uncommon. You possibly won't see them very often. Okay, so like I said, we'll look at transposing in the previous slide. So transposing is essentially swapping the rows and columns of a matrix. And this can be easily done even just by hand, or you can also use your CAS. So if you were to do this on CAS, for the white CAS, I'm pretty sure there's a specific function in the matrix menu called transpose. However, if you were doing it on the TI Inspire, you would just put the matrix. So you would write the matrix, and then you would put it to the power of T to find the transpose of the matrix. It's like this. So essentially the transpose is where you're essentially swapping the rows and the columns. So the rows, so this row, this column, so column 1 would become row 1 of the new matrix. And column 2 would become row 2 of the transposed matrix. So pretty straightforward. And another thing to note is when you're transposing a matrix, the order is also going to change. So if we had a 3 by 2 matrix, it would now be a 2 by 3 matrix. So essentially the rows are swapping, the rows and columns are swapping. Okay, so now we'll move on to matrix arithmetic. So matrix arithmetic will be covering addition, subtraction, and multiplication of matrices. So addition and subtraction are pretty straightforward. Just a few rules that you need to sort of memorize or sort of know is that if you're adding or subtracting matrices, you need to have the same order of matrices. So the matrices need to have the same order. So for example, in this question, we have a, so 2 rows, so 2 by 3 matrix, and then we're adding it to a 2 by 3 matrix. So since these two matrices have the same order, they can be added. So when you're doing matrix addition and subtraction, the first thing to know or to sort of find out is if the matrices that you're adding or subtracting have the same order. If they don't have the same order, then the addition or subtraction cannot actually be done. So in matrix and matrix addition and matrix subtraction, all that we're doing is we're adding the elements in the same position in the 2 matrices or the 3 matrices that you're adding. So for example, when we're adding these 2 matrices, what we're doing is we're adding the elements in the same position. So for example, in position 1, 1, or first column, first row, we're adding that to the element in the first column and first row of the other matrix. So these 2 elements will be added together. And the final matrix will also have the same order as the 2 matrices that you're adding. So this will also be a 2 by 3 matrix. And essentially when you add these 2 numbers, so 3 and 3, in the same position on both of the matrices, the final or the sum is going to be in the same position as well. It's just going to be the addition of these 2 elements. So 3 plus 3 gives you 6. Similarly, if we were to add the elements in the first row and second column, so 7 in this matrix and 9 in this matrix, so 7 plus 9 would equal to 16. And that would be in the same position as these two elements in the new matrix. So pretty straightforward. We're just adding the elements in the same position when we're adding matrices, and that will be the new position, or the position of the sum of the two numbers. Same for subtraction. So subtraction is exactly the same. So if this was subtraction instead, we would just do 3 minus 3 instead of 3 plus 3, and the position would just be row 1 and column 1 for the answer, which would be 0 in this case. And that's how you would do matrix addition and subtraction. So let me know if you have any questions so far in the chat. Okay, so next we'll move on to matrix multiplication. So matrix multiplication is a little bit different, but essentially it can be done on your CAS, and Weka will usually, most of the time, won't really expect you to do it by hand, but it's really important to be able to do it by hand because, and I'll show you why that's the case. So we'll only be doing matrix multiplication because matrix division cannot be done. It's not really a function that can really be done for matrices. There's another way that we can sort of technically divide matrices, but it's not conventional as dividing two numbers. It's like 8 and 2. If we were to divide 8 by 2 to get 4, it's not as simple as that. So we'll get to that later. Okay, so when you're multiplying matrices, there's essentially two rules that you need to sort of work out before you start the actual multiplying. So the first thing is that the order for the order of the matrix multiplication needs to be sort of worked out. So you need to work out the order of the two matrices that you're multiplying before you do the actual multiplication. And the essential rule is that the number of columns in the first matrix must equal to the number of rows in the second matrix. So this is really important. So essentially, if we had matrix A and we wanted to multiply it by matrix B, the other way around, B times A. Another thing that you need to remember, understand is that multiplying matrix B by A is not the same as A times B. So A times B is not the same as B times A. The order is so important. And I'll show you why in a second. So if we were to multiply matrix B by matrix A, what we would do is we would find the order of both of the matrices. So for matrix B, it's just 2 rows and 1 column. So 2 by 1. And then what we do is we put an X in the middle, and then we write the order of the second matrix. So second matrix is A, which is a 2 by 2 matrix. So once we write it in this form, so the order of the first matrix multiplied, or not multiplied, but X, the second matrix, the order of the second matrix. Then what we do is we put brackets around the inside numbers. So around this number and around this number, we would put a bracket. And now what you need to check is if these two numbers are the same. So in this case, these two numbers are not the same. So we have a 1 and we have a 2. So that's not the same. So what that tells you is that the matrix multiplication cannot be performed. So the answer is going to be undefined, or it just can't you just can't do the matrix multiplication. And that's because the number of columns, so 1 represents the number of columns in matrix B, in the first matrix, must equal the number of rows, which is 2, in the second matrix. And if it's not the same, then the matrix multiplication cannot be performed. So that's the first rule. So if we were to do A multiplied by B instead, so then we write the matrix, the order of matrix A first, so 2 by 2, X, the order of matrix B, 2 by 1, and then we put the brackets inside the around the inside numbers. So that would be 2 and 2. So in this case, they're both the same. And since they're both the same, we can perform this matrix multiplication. So that's the way that you need to verify if the matrix multiplication can be performed or not before actually doing anything else. Okay, so that was the first rule essentially. The second rule is that if the matrix multiplication can be performed, and that the number of columns in the first matrix is equal to the number of rows in the second matrix, so 2 times 2, if it's the same number, the second rule states that the number of rows is going to be the same as the first matrix, and the number of columns is going to be the same as the second matrix. So the outside numbers, so the numbers that are not put in the brackets, are going to be the new order. So the new order of this matrix, so once the multiplication has occurred, is going to be 2 times 1. So multiplication is a little bit different to addition or subtraction. You're not just going to multiply the numbers in the same position. It's a little bit different. You need to sort of use these two rules before you do the matrix multiplication. So first step is working out if the matrix multiplication can even be performed by writing down the order in this form and then putting a bracket inside the inside two numbers. So in this case, if it's going to be 2 by 2, that means the matrix multiplication can be performed. And then the order is just going to be the outside numbers. Okay, let me know if you have any questions. Okay, so now we're actually going to do the matrix multiplication. So in the previous question, we verified that the matrix multiplication will exist if we multiply A by B. So now we will do the actual matrix multiplication. Excuse me. So the actual process for multiplying is a little bit weird when you first start doing it. But once you start doing it, it becomes really easy. So the way that we do matrix multiplication is we take the numbers in the first row and we'll multiply that by the numbers in the first column of the second matrix. So what we do is we do 1 times by 5. So the number in the first row of the first column multiplied by the first number in the first row of the first column in the second matrix. And then we take the number in the second column and then we multiply by the number in the second row. And then we add those two together. So 1 times 5 added by 3 times by 6. And that becomes the new element in the first row and first column of the product matrix. And then once we've done that, we do the exact same process. So we take the numbers in the second row and then multiply by the numbers in the first column. So if there's multiple columns, you'll have to do this process a few times. But essentially, first row times first column, second row times first column, then first row times if there's a second column, second row times second column, and so on. So this can get really messy really quickly. So that's why it would be beneficial if you could do this on your calculator. And VCA will usually expect you to do it on your calculator, except for a sort of few times when they actually ask you, instead of asking, okay, so the thing is, VCA can't actually really verify if you've done it on your CAS or by hand. So there's no actual point in putting in a question which asks you to do it by hand, because they don't actually, like, it's usually most of the questions in the exam are 1 mark, or 2 marks most of the time. And they're really, what they're going to be doing is just asking you to, if they give you these two matrices, just work out what this matrix is. So just write the actual final answer using a calculator. But what VCA likes to do in order to test this is what they'll ask you to do is say, how did you find this element? And then is when you will show this particular working out. So 2 times 5 plus 4 times 6. So if they were to ask you, how did you calculate element? So let's just say this product matrix was called A. And they will ask you to work out, how did you find our element, element 2, 1, So element 2, so element in row 2, column 1 of the product matrix, and they ask you to show your working out of how you found this element in the product matrix. So in that case, you would need to show this working out over here. So 2 times 5 plus 4 times 6. And that is how they can verify that you've done this by hand. Or well, not by hand, but that you know your sort of principles of matrix multiplication. If you have any questions, let me know in the chat. We're going to move on to summing matrices. So matrix multiplication is really important. And basically, you need to follow those 2 rules at the beginning to verify if the matrix multiplication exists. And if it exists, you can either use your calculator or just use the process that I've just went through. But the process can get really complicated sometimes. So prefer to use your calculator, but also keeping it at the back of your mind of how you would do it by hand, in case there's a question like the one that I just showed you. Okay, so next we'll move on to summing matrices. So these are essentially matrices that we will use if we wanted to, for example, add up the numbers in a particular row or a particular column. So if we wanted to add the values of the numbers in a particular row, we would use a row summing matrix. And a row summing matrix is essentially a column matrix that just contains ones. So the elements are just ones, and the amount of and the size of the column matrix that you would use is dependent on the size of the original matrix that you're trying to sum up. So what I mean by that is, if the numbers in each row, if there's 2 numbers in each row, then the row summing matrix that you're going to be needing will have 2 rows as well. And since it's a column matrix, it's only going to contain 1 column. So only contain 1 column, all the elements are going to be 1, and the number of rows is going to be the same as the number of sort of columns in this matrix, because you're going to add up 4 and 5, so the number in each row, so you'll need 2 elements in the row summing matrix. And the specific order of where you place this matrix is really important. So you can't do 1, 1 times by this matrix. So if you're using a row summing matrix, you'll need to put it after the matrix that you want to sum up the rows for. So yeah, you do the row summing matrix and then multiply by the column matrix. So the order is really important. However, if you want to sum up the columns, so 4, 8, 9, 5, 1, 0, if you want to add that up, what we would do instead is use a row matrix. So the row matrix would have the same number of columns as the number of rows that you want to add up. So in this case, we want to add up 1, 2, 3 rows. So therefore, there will be 3 elements in the column summing matrix, or the row matrix, but only 1 row. And this time, the column summing matrix will need to be placed in front of the matrix that you want to add the columns for. So that's really important. Jot this down somewhere in your summary book, and you should be really good to go. Okay, so now we'll have a look at scalar multiplication. So scalar multiplication is a little bit different than matrix multiplication, because in scalar multiplication, you're multiplying the matrix by just 1 number. And it's a scalar, it's not a matrix. So for example, just multiplying this matrix by 1.2, for example, that would be scalar multiplication. However, if this was a matrix, so matrix times multiplied by a matrix, then that would be matrix multiplication. And you would have to use the other method that we just went through a few slides back. So when you're doing scalar multiplication, all you need to do is multiply each element by the number, by the scalar, essentially. So for example, here, the scalar is 1.2, so you'll need to multiply each element by 1.2, and that will be your product matrix. And the sort of uses of scalar multiplication are usually financial reasons. So for example, if we have a particular item at a store and we want to mark up the price by 20%, we might use a scalar multiplication. So for example, if we had the values or the the prices of the items in a matrix. So like I said, matrices are just another way of representing information. So if we had the prices of various items in a store in a matrix, and we want to mark up the price, we can just use a scalar multiplication, or a scalar, so 1.2 in this case, because we want to mark up the price by 20%. And that will give us the new price. So sort of similar to, if we go all the way back to Unit 3, sort of similar to seasonal indices. So very similar to that. And then another thing that you need to know is matrix powers. So that is when so this is probably not that often. You won't see this very often, but just in case, if we're putting a matrix to a power of something, so for example, a to the power of 2 or a to the power of 3, it's not just as simple as putting all the numbers in the element to the power of 3. Because if you remember back to high school, or back to the beginning of high school, if you're doing 2 to the power of, let's just say 3, that's not just, so that's actually equal to 2 times 2 times 2. So if we're doing a matrix, for example, a to the power of 3, that would actually be matrix A times matrix A times matrix A. So just really important, but most of the time this will all be done on your CAS. So just in case there's a question where you have to do it by hand, this is what it actually means. Okay. So now we'll talk about permutation matrices. So like I said, permutation matrices are really important in the course. But the main uses of permutation matrices in matrix arithmetic is usually to manipulate a particular matrix without actually changing the elements. So usually what we use a permutation matrix for is to change the order of a matrix. Sorry, not the order, but the order of the elements in the matrix. For example, if we have in this matrix rat, and instead we want tar, in order to change that order using some form of matrix method, we would need to use a permutation matrix. And usually what VCA likes to assess in terms of this topic is they will give you a matrix and they will ask you to find the permutation matrix that will take you to the new matrix, or whatever they asked you to find. And this is a little bit of CAS, so you need to be really good at using your CAS for this. And it's also a little bit of trial and error. Like there's no specific method, I would say, that you would use, that you would sort of use to do this question. It's a lot of trial and error. But the way that I like to sort of do these types of questions is I like to write from and to in my matrix. So from and to. So the way that I like to sort of work with this is if I have a particular permutation matrix, so remember a permutation matrix is always a square matrix and it only contains 1, 1 in each row in each column. It's different to a binary matrix because binary matrices just contain zeros and ones. They might have more than 1 in each row or each column, but a permutation matrix will only contain 1 in each row and each column. So, for example, the way that I like to think it is if we have something in row 1 and we want to change it to column 3, we want to place the 1 in the third column because we want to place it in the third row. So the way that this would sort of work in terms of matrix multiplication is, if you think about it, it's going to be 0 times R, 0 times A, plus 1 times T. So therefore, T would be placed in the first row of the new matrix. Similarly, we have 0, 1, 0. So 1 is in the middle, or in the second column. So therefore, A would be placed in the second column of the new matrix. So it will retain its position. Whereas for this one, in the third row, we have 1 in the first column. So therefore, R will be placed in the third row instead. So this number, so wherever the 1 is, would indicate where the number would go. So for example, in this matrix, in the first column, we have a 1 in the third row. So therefore, R, which is in the first row, would go into the third row. Similarly, we have A in the second column and the second row. So therefore, it would go in the second row of the final matrix. And T, which is in the, so we have a 1 here, which is in the first row and third column. So therefore, T would go into the first row. So a little bit of trial and error if you're using your CAS. So try doing a lot of various different permutation matrices. Try multiplying it with RAT to get to TAR. So a lot of trial and error. But you will eventually get some. So this is not something that would be really hard, but something important to know is that you're using a permutation matrix. And the permutation matrix is actually, when you're multiplying it, it comes before the matrix that you want to change the order of. So just a few important things to know if you are going to be using trial and error. Okay, so next we move on to matrix equations. So matrix equations is essentially another way of dividing matrices. So like I said, you can't divide matrices. There's a different method that you will use in order to divide matrices, but we're essentially not dividing, as you will see very soon. And there's something called matrix equations. So for example, if we had A times X is equal to B. So let's just say they're not matrices, they're just common letters. So if we want to find X, all we will need to do is divide by A on the right-hand side. But we can't actually do that in terms of matrices. So we'll have to use a different method, and that's called matrix inverses. So we'll need to find the inverse of this matrix and then multiply the matrix here by the inverse of this matrix in order to find what X is. It's a little bit complicated, but I'll try and break it down. Okay. So first step is finding the determinant matrix. So the determinant of a matrix. So the way that you would find the determinant of a matrix is by using this particular formula. So A times D minus B times C. So and for the purposes of general maths 3-4, you'll only be finding the determinants of 4 by 2 by 2 matrices. So square matrices that are 2 by 2. You can on your CAS, however, find the determinants for 3 by 3 matrices, but VCA won't be testing that. They'll only be testing the determinants for 2 by 2 matrices. So you will label your elements. So for example, if you had this matrix over here, so if you had this matrix over here, so 2, 3, 4, 5, you will then have to label your matrix. So 2 will be A, 4 will be B, 3 will be C, and 5 will be D. So once you've done that, then you can use a formula. So determinant is just A times D, so 2 times 5 minus B, which is 4, times 3. So in this case, the determinant is going to be 2 times 5 minus 4 times 3. So that will be 10 minus 12, which equals negative 2. So once you've found the determinant, there's two things that you need to sort of identify. So the thing that you need to look out for if the determinant is equal to 0. And if the determinant is equal to 0, that means the inverse does not exist. And if the inverse does not exist, that means the equation can't be solved. And the other thing is if the determinant is not equal to 0. So if it's not equal to 0, such as in this case where it's equal to negative 2, that means the inverse can be found. And if the inverse can be found, you will be using this formula. So VCA does not expect you to find inverses, or most of the time, by hand. So you will be using your CAS most of the time. So to find the CAS, all you will need to do is have your matrix and put it to the power of -1 on your CAS. And that will give you the inverse. But if not, there's this formula. It's also in your formula sheet. The formula is -1 over the determinant of the matrix, so what you've just found, and then the matrix. And the order is sort of reversed. You have D and A being flipped, so in this case, the 5 and the 2 being flipped, and the B and the C just being negative. And that's how you would find the inverse. A little bit weird, but pretty straight. But just using your CAS would make it really straightforward. Okay, so once we've found, so this is the equation, so just a practice question. Step 1 is finding the determinant. So in this case, it's 4. So since it's not equal to 0, that means the inverse will exist and that we can solve the equation. Next step is finding the inverse. You can do this easily on your CAS, if not using just the formula, and that will give you this as the inverse matrix. Now to find the inverse, you will actually be using one of two different methods. So if the equation was A times X is equal to B, to find X, it will just be A inverse times by B. However, if it was X times A is equal to B, then X would be B times A inverse. So the order is really, really important. So in this case, it was A times X is equal to B, so therefore X is equal to A inverse times by B. So pretty straightforward, and once you do that, you should get what X is equal to. And remember, these types of questions are something that you would do on your CAS most of the time. Okay. So next, we also have simultaneous equations. So this doesn't really appear that often on the exam, but sometimes there will be situations where you will have to formulate simultaneous equations. So you probably would have seen simultaneous equations before, but essentially equations involving two different variables. So you have two different variables and you have two different situations. And then you will use matrices, so you'll convert this equation into a matrix such as this, for example. So for example, we have A times X is equal to B. So if we were to convert these two equations into a matrix equation, all we will need to do is take the equation, so 4, so 4, 2, so those are here, and then 3 and 2 over here. So they usually run like this in the matrix. So if you were to sort of spell out the equation, it would actually just be 4x times 2y is equal to 5. And then 3x times 2y is equal to 2. If you were to actually multiply it. But we're not trying to do that. We're trying to find out what x and y is equal to. So essentially what we would need to do is, again, find the inverse of A. So x is therefore equal to A inverse times by B. And that will give you something like xy equals, let's just say, after I've found the inverse and I multiply it by 5 over 2, I get 11/6, let's just say. So what this tells you is that x is equal to 6 and x is equal to 11 and y is equal to 6. So you can also solve this on your CAS if you know other functions, but matrices are always a really good way, and sometimes your SACs and your exams will be structured in a particular way that will ask you to use matrices to solve the equation. Okay, so then we have cost matrices. So this is essentially a practice question for everyone to do. So we have a cost matrices for 3 different types of clothing. So P is the cost matrix. So A costs $14, for example, B costs $26, and C costs $9. And we want to create a permutation matrix. So I've sort of didn't tell you the whole truth about permutation matrices, Permutation matrices don't always contain zeros and one. Most of the time it will. But sometimes it can contain other numbers as well. But the important thing to note is in each column and each row, there will only be one number. The rest are going to be zeros. So if you're watching the live stream, I'm now going to go through solutions for this question. But if you're not, I would love it if you could pause and maybe have a go at the question before I go through the solutions. So essentially what we're doing in this question is we are marking up the price of these items, or marking down in some cases. So for example, A, we want to increase by 10%. B, we want to reduce by 20%. And C, we want to reduce by 8%. So this would be the answer here. So we have the cost of the items, and then we multiply it by the permutation matrix. So essentially the way that this would sort of be done is 14 times by 1.1. So it's again a little bit of trial and error. There's no specific method that you can reliably use for these types of questions. But essentially if you have 14 times by 1.1, so if you do the sort of multiplication steps, you'll usually get to the final or the correct answer. Or you can sort of use that sort of theory of multiplication. So we'll have 14 times 1.1 plus 26 times 0 plus 9 times 0. So if we were to multiply this matrix, we'll get, razor. You will get 14 times 1.1 as your first element. And this is actually what we want, because we can't multiply by a scalar. Because if we were to multiply this matrix by a scalar, we can't multiply by one particular scalar, because what we would be doing is essentially ending up with all of these numbers multiplied by 1.1, because we want to increase the price by 10%. So this is a smart way of doing this, so that we only multiply the number we want to multiply by 1.1. So 1.1 times 14. And if we do the matrix multiplication step, it would be row 1 times column 2. So only 26 will get multiplied by 0.8. Because 14 times 0 plus 26 times 0.8 plus 9 times 0. And in that way, only 26 is getting multiplied by 0.8. So most of the time, students can get what the scalar is going to be, but they don't actually know how to set up the permutation matrix. So that's the important skill that we're sort of going over right now. And same for the third one. So so if we were to do the third step of the matrix multiplication, so 14 times 0, 26 times 0, plus 9 times 0.92. So only multiplying 9 by 0.92. So it's a very smart way of doing it, but I would recommend using trial and error on your CADs to sort of work it out. Okay, so we finished essentially matrix arithmetic. Now we're going to be moving on to communication matrices. So communication matrices are again another way of representing a type of information. And this time it's usually a communication system which consists of a sender and a receiver. So essentially what happens is we have a sender and a receiver. And this can be either directed or undirected communication. And I'll go through that in the next slide. So essentially what this matrix is essentially telling you is if there's a 1 in the matrix, that indicates that the sender can can communicate with the receiver. Whereas if there's a 0, so for example, B and C, if we look at the union of B and C, there is a 0. So that means B, who is the sender, cannot send a message to C. So it's a little bit strange sometimes, because if C can send a message to B, why can't B send a message to C? But that's just how it is sometimes. So here is just a few examples. So we have the sender and the receiver. So B is the sender and C is the receiver. If we look at their union, where they sort of come together at this point, there's a 0. So that means B, who is the sender, cannot send a message to the receiver, or he can't communicate with the receiver. Whereas here, we have the sender C and the receiver B. So if we look at their union here at 1, so if there's a 1, that means C can send a message to B, or it can communicate with B. So if we were to look at a random one, for example, this one over here. So B, who is a sender, and A is the receiver, and there's a 1 here, so that means B can send a message to A. So this is how we essentially read a communication matrix. Okay, and there'll be a few calculations involved with this as well, but the important part is knowing how to set up the communication matrix. Okay, so now we'll go through directed and undirected matrices. So essentially, directed communication matrices is when, so like what we were looking at just before. Sorry, this is a little bit messed up in the formatting. Just ignore that. So it's A, B, C, D, E. So essentially, a directed matrices is when one person can communicate with the other person, but it doesn't go both ways. And it will be usually, so we usually have network diagrams as well. So I don't think I've, so this is like just treated as sort of like an introduction to networks, our next topic. So a network diagram is just another way of representing this information in a more visual way, whereas matrices is usually representing the communication systems in a more mathematical way. So what this diagram indicates is that B can communicate with A. So this is indicated by the arrow. Here we can see there's the arrows are both directions. So therefore C can communicate with A and A can communicate with C. However, this is called a directed matrix because we have arrows. And as compared to a undirected network, we don't have arrows. So what this means is if there's a link between B and A, it means that B and A can communicate with each other. So it goes both ways. And this is usually the case in real life scenarios. For example, you can send a message to your friend and the friend can send a message back to you. This might be something like, for example, I don't know. I can't really think of a typical example for this one, but for example, somewhere in a, like a job, for example, or a certain, I don't know, for example, in a certain position, a person can send a message to their boss, but their boss can't send a message back to them. Or you can send a message to someone in a higher position to you, but they can't send a message back to you, or the other way around. It just depends on what the situation is. But most of the time you'll be seeing undirected communication matrices. And the way that they work is essentially what I've just gone through in the previous slide. So if there's a 1 here, that means that the sender can communicate with the receiver. And in a communication matrix, the sender and receiver will be very clearly labeled. So it won't be ambiguous at all. So sender's usually on the left-hand side and the receiver's usually on the top. So it'll be very clearly labeled for you. Okay, next we'll move on to two-step communication. So two-step communication is essentially looking at communication networks where it's conducted in 2 steps. So for example, if E wants to communicate with A, it might send a message to D, who can send that message to A. So that's a two-step communication because it's conducted in 2 steps. A single step is what we were just looking at, where E is communicating with D. And to find the two-step communication matrix, or a matrix that gives, so for example, if there's a 1 here, this one here. So if there's a 1 here in a two-step communication matrix, what that essentially tells you is that B can communicate with A in 2 steps. So this is actually the 1-step communication matrix, but if it was the 2-step communication matrix, that is what it would indicate. And in these types of matrices, we can also have more than one number. So we can have 1, we can have 2, if there's 2 parts. Same for 1-step communication matrix, because sometimes a person can communicate with another person via 2 means. For example, just as an example, for example, if we had another path over here, that would be a 2 for the number of ways that B can communicate with A. because it can communicate why this means and why this means. And to find the two-step communication matrix, so you can work through it and work out how many two-step communications there are, but the best way is to find the two-step communication matrix. So the way that you find the two-step communication matrix is by putting the one-step communication matrix to the power of 2. So you square the initial communication matrix, and you will do this on your calculator to find the two-step communication matrix. Okay, so if we were to just look at an example, so if there's a 2 here, what that means is, so I think this is E, and this is A. So what that means is E can communicate with A via 2 ways through two-step communication. So one would be maybe E to D to A, and the other one might be E to C to A. So that's why there's a 2 there. So that's just how you would read the two-step communication matrix. Okay. And then we look at total communication. So total communication is not that important for communication matrices, but sometimes they will ask you to calculate that. And the way that you would find it is to add the one-step communication matrix with the two-step communication matrix. And again, this is something that you would do on your CAS. So adding the one-step communication matrix with the two-step communication matrix will give you the total communication matrix. And that's pretty much straightforward. There's not many uses for this particular type of matrix. But now we'll move on to dominance matrices, and here it will have a certain use. And what dominance matrices essentially are used for is, for example, a competition or a round-robin tournament. So essentially what it indicates is, for example, if a lot of teams are versing other teams, we want a way to sort of represent what team is winning and what team is losing. So here we'll have a winner and a loser. So the way that we sort of interpret this is, if we have a 1 here, what that means is that if Team C was versing Team B, Team C is going to be the winner, and Team B is going to be the loser. So that's the dominance. So the one on the left is going to be, so if there's a 1, so if there's a 0, for example here, what that means, actually that's a bad example. So this one over here. Ooh. Sorry. Okay. So if there's a 0 here, what that means is if B is versing C, B is going to lose and C is going to win. So that's how you would interpret this type of matrix. So very similar to communication matrices, but just get really used to the headings and what they mean. Okay, so then we can also have two-step dominances. So two-step dominances is very similar to two-step communication, is when one team versus another team who has bet another team. So very sort of confusing, but again, the way that you would find the two-step dominance matrix is by squaring the one-step dominance matrix. So first you would have to construct the one-step dominance matrix and then square it to find the two-step dominance matrix. And what this 2 shows here is, for example, it was A and B. Just as an example, if it was B and A, what this indicates is that B has bet a team 2 times that has also bet A. So for example, it might be B has dominated C, which has dominated A, and it might be that B has dominated D, which has dominated A. So this is what the 2 would indicate in that situation. And then we have total dominance. So total dominance here does have a particular meaning. So once we find the total dominance matrix by adding the one-step dominance matrix and the two-step dominance matrices, we will get the total dominance matrix. And the way that we would use the total dominance matrix is we would find the overall dominance. And the way that we would do it is we would add the numbers in each row. So here we have a 3, here we have a 5, a 4, and then a 2. So once we've added all the numbers in the rows, what we then need to do is find out the order. So B, which was this row here, is a 5. So therefore B has the total dominance, or has bet the most number of teams. And then a 4, and then a 3, and then a 2. So that's how you would find the overall winner in a competition like this. Okay, so now we're going to move on to transition matrices. Okay. Sorry. So I skipped a slide. Yeah, so now we're going to be moving on to transitional matrices. So transitional matrices are just a way of sort of using the past and the patterns in the past to predict a future. And so they can either be really simple transition matrices like this. So for example, if you're at position A today, you will go to position A tomorrow. And if you're at, for example, position B today, you'll go to position C tomorrow. And then if you're at position C today, then you'll go to position D tomorrow. So that's essentially what you would read this type of transition matrix. So very similar to communication matrices. But these are not the type of transition matrices that we really sort of use. So I'll come back to this. Okay, so this is the sort of transition matrices that we would look like. And it's mostly used for like stuff like populations and other types of changes. And it's just used to sort of predict the change in the future. So for example, if we have, for example, 2 locations in a school, the oval and the canteen, what this network would indicate is that 30% of people would change their position from today to tomorrow, from oval to the canteen. So for example, if we had 10 people going to the oval today, so tomorrow 30% of those will go to the canteen and 70% of them will stay at the oval. And if we look at the other way around, it would be 40%. So canteen, if we had, let's just say 15 people at the canteen today, 60% of those are going to go to the oval tomorrow, whereas 40% of them are going to stay here. So that's how you would sort of, and they'll usually depict it using these types of diagrams. So it might be 2 places, it might be 3 places. And then from there, we could convert this into a transitional matrix. And the way that we sort of use this matrix is we have a to and a from. And essentially we just plot that information. So going from 2 to O, it's 0.7 because 70% are going to stay at position O, or the oval. And from C to O, it's 0.3. So it's this one over here. So from C to O. I think from C to O. I think this is sort of like, actually no, sorry, that makes sense. So going from C to O, it's 30%. So hopefully that makes sense, and this is how we would sort of determine it. And then we would use state matrices. So this is sort of like a throwback to financial maths where we're using recurrence relations. So we would essentially use transition matrices to sort of predict the future, or to sort of predict the number of people that we might have, for example, the oval or canteen over time. So after 15 days, after 10 days, after 20 days. So that's what we would, and I'll go through an example. So for example, in this matrix over here, we have the transition matrix that we just formed. And the important thing to note is the columns always add up to 1. Regardless of how many positions you have, the columns will always add up to 1. So that's something really important to know, and what we love to test. Because they might give you an uncompleted diagram and give you something, to fill in. Okay, so if we have initially 50 students at the oval, so let's just say it's a Monday morning, and we have 50 students at the oval and 70 students at the canteen on day 1. So then we use this initial state matrix, or S naught. So the initial statement, so for example, if we're using financial maths or referring back to financial maths, we might use V naught to refer to, for example, the initial sum of money that we put in the bank. So same here, we have an initial state matrix. So initial, we have 50 at the oval and 70 at the canteen. And then if we want to find the sort of numbers of people on day 2, we need to find what S1 would be. Because S0 is day 1, S1 would be day 2. So all we need to do is matrix, the transition matrix, multiply by the state matrix. And once we do that, we will get the S1, or the proportion of people, or the number of people actually, on day 2. So we have 77 on the oval and 40 on the canteen. And we can do this for however many days we want. And for that, we would use the nth term rule. So it's very similar to financial maths. So it's really hard to use to use recurrence relationships if you were to, for example, predict the number of people on after 50 days. Because then you would need to find the first one, the second one, the third one. Instead, you can use t to the power of n times s to the power of n, or s to the power of 0. So the way that we would use this is, if you want to find s to the power of n plus 1, it would just be the transition matrix to the power of n times by the initial state matrix. So very similar to financial maths. So for example, here we want to find the number of people on the 6th day. So that will be s to the power of 6, which is equal to transition matrix to the power of 5 times by the matrix. Again, you would do this on your CAS. So very straightforward. And then we'll have a look at the steady state. So the steady state is essentially the point. So all transition matrices will reach a steady state. And the steady state is the point where the values stop changing. So after like maybe 50 days, the number of kids at the oval and the number of kids at the canteen are going to stop changing. It's going to be 80 every day and 40 every day. And that's also called equilibrium, where the values sort of reach a point where they don't change anymore. And all transition matrices are going to have this. And to find the steady state, what you need to do is find the sort of number of kids after not the number of kids, but the number, matrix after, for example, 50 days or after 51 days, like a really high number, usually greater than 50. And then you would find it, let's just say after 50 days, it's going to be 80 students at the oval and 40 at the canteen. And then what you need to do is to prove that this is the steady state, steady state, is that you would need to find the 51. So you would need to find the the state matrix on the very next sort of day. So the immediate after, so 51st day. And if that is the same, that means that this is the steady state matrix. So that's essentially how you would prove it. So you would find the the state matrix for a really late date, for example, after 50 days or after 51 days, choosing a really large n value, and then you would find it for the consecutive n value. So if we chose 50, then we would need to find it for the 51st day. If we chose 60, then we would need to find it for the 61st day. If they're both the same, then that means we have a steady state matrix. Okay, and then we can also have culling and restocking. So what culling and restocking essentially is instead of it just being, the same number of students at the oval and the canteen, this is like the beginning of the school year and we're getting new students coming in every week or every day. So what might happen is some students might be removed, so that's culling, when we're removing values after each sort of addition. So for example, if we were to relate it back to financial maths, if we have an annuity and we're removing a certain amount of money after each period, as we're taking a payment, that would be, for example, culling. We're taking a value after the interest is added. So sort of this exact same thing. So after after day 1, a certain amount of students might, go away from the oval or the canteen, they might choose a different location completely, and some students might come in and might choose either of those situations. And then the way that we sort of represent this is, so we have, for example, something like this. So after we find, for example, if we're finding S1, we have 25 cows being added. So 25 tan cows being added. Actually, I'll go through the whole example so we can understand. So a farm has 50 tan cows, 50 black cows, and 50 white cows. A transition matrix is provided below. Each generation, the cows mate and new quantities arise of each. So these new quantities of cows that are being added are not the ones that we include in the culling or restocking. These are the ones that we would include. So 15 white cows that are being added or being purposely bought. So 15 white cows, 10 black cows are removed for selling, and 25 tan cows are being added. So essentially it would look something like this. So we have the transition matrix. We would have the S0 matrix or the SN matrix. And the important thing to note for this is, similar to financial maths, if you have something like this, you cannot use recurrence. You cannot use the nth term rules. You can't use t to the power of n. You'll have to use the recurrence relations. T as the power of n plus a. So that A matrix would represent the change. So we're adding 25 tan cows. We're removing we're removing 10 black cows, and we're also removing 15 black cows. So that's how you would write that down, and then you can put it on your calculator to get the new value for S1. Okay, so now we'll move on to Leslie matrices. So Leslie matrices are the only new and added content to the study design. They're essentially the same thing as transition matrices. It's just that the way that you would use them is a little bit different, and also what they represent is a little bit different. So Leslie matrices look at the change in the female members of a particular population over time. And if you think about it, we will have some form of survival rate and birth rate. So if we have, or if we're analyzing different age groups in a female population, so for example, if we were analyzing, a particular insect population, we might look at, 1 week-year-old insects, then we might look at 2 week-year-old insects, and then we might look at 3 week-year-old insects, and that might be the life cycle of the insect population. So they might just die off after 3 weeks. So in that case, what will happen is we would have a birth rate and a survival rate. So going from week 1 of the insect population to week 2, we might have only some of the insects going into the next stage. And then from week 2 to week 3, we might only have a certain population, a certain proportion of the population that might be going from the second age group to the third age group. And then from the third age group, we don't really have a survival rate because they're all going to die off after 3 weeks. And then the other thing that we have a look at is birth rate. So birth rate is how many females, so on average, how many babies are being born per female in each age group. So for example, in a particular population, so the insect one, so in the first week, the insects are not mature enough to give birth. So the birth rate is going to be 0. In the second stage, so in the second week, the insects are mature enough, so therefore they can give birth. And the birth rate is, let's just say, 5. So each insect mother is going to give birth to 5 babies so on average. So that the birth rate would be 5. And the, let's just say the third week, it might be 2. So stuff like that, you'll have a birth rate and a survival rate. So survival rate just refers to what proportion of females are going from one age group to the next age group. And then the birth rate is, on average, how many females are being born, per female in each age group. Because remember, we only look at the female of the population. And these can take the form of nth term-like equations. So again, very similar to transition matrices. So I'll go through an example now. And the only thing that you will notice is different is that the columns will not necessarily add up to 1. So in transition matrices, they're always added up to 1. In these types of questions, they won't add up to 1. And this is an example of a Leslie matrix question. So we have usually a life cycle transition diagram. So this diagram over here is called a life cycle transition diagram. And essentially what's happening is we have age group 1, age group 2, and age group 3. You might have more age groups, you might have less age groups. And then from age group 1 to age group 2, we have a survival rate of 0.5. So only 50% of the insects in age group 1 are going to survive to age group 2. And then from age group 2, 60% of them are going to survive to age group 3. And then after age group 3, since they all die off, we're not going to have any other survival rates. And then these ones over here, as well as this one, represent the birth rates. So for example, in this population, so it's rats. So anyone in week 1 is already mature enough to give birth. So on average, for each female in age group 1, 0.6 rabbit babies are born. And it's a circle because if we look at the females born, they're going to be born in age group 1, right? They're not going to be born in age group 2 or age group 3. Because if we're giving birth to someone, they're going to be born as, you know, in age group 1 or the youngest age group. So for example, 2.4 would represent the birth rate for any female in age group 2. So it goes back to 1 because the rats that are going to be born are going to be born in age group 1. And then 0.7 for age group 3. And this is how you would construct the Leslie matrix. So again, you would have, so I would say probably a from and a to. So on the top row, you would have all your birth rates. So age group 1 birth rate, age group 2 birth rate, age group 3 birth rate. If there's 4, age group 4 birth rate. And then all of your survival rates are diagonal. So below the first row, they start diagonal. So survival rate of age group 1, survival rate of age group 2, depending on how many age groups you have. And if you have 3 age groups, the matrix is going to have an order of 3 by 3. So that's really important to note. And we're also going to have, very similar to transition matrices, we're going to have an initial population, and then we might be required to calculate the population after 6 years, for example. So then you would put it to the power of 5 and calculate the matrices, the answer. So this is the answer here. Next step is to calculate, so this would be the individual population of rats in each age group after 6 years. And since we're calculating the total female population of rats after 6 years, then you might use a summing matrix to calculate the number of female rats. So very straightforward, very similar. So what's a straightforward, but very similar to transition matrices. Okay, so that was essentially it for matrices. Now we're going to be looking at networks, and I've also included the VCA dot points for networks. So I'm not going to go through all of them, but basically we're going to be looking at shortest path problems. We're going to be looking at network representation. We're going to be looking at minimal spanning trees. We're going to be looking at flow problems. We're going to be looking at the Hungarian algorithm. And we're also going to be looking at forward and backward scanning for any project type questions, and also a little bit of crashing. So we're not going to go through a lot of crashing today, but you will have a look at the basics of crashing. Okay, so what is a network? So like I said, a network is just another way of representing information. So we can have different types of networks. So first we'll look at just undirected networks. So undirected networks are ones which have no arrows, just lines connecting the different vertices. So these things, the individual points, are called vertices, or the vertex. And we have lines connecting the vertexes to represent certain relationships between the vertices. And those lines are called edges. And if we have an edge that's connecting one vertex to itself, it's called a loop. And if we have a vertex that's not connecting any of the other vertices in the network by an edge, it's called an isolated vertex. And the thing that we look at for vertices is their degree. So the degree of a vertex just refers to how many edges are connected to that vertex. And the vertex, so for example, in this one over here, So for example, this vertex over here would have a degree of 3 because we have one, so we have one edge here, one edge here, and one edge here. So 3 edges. So therefore the degree of this vertex will be 3. And this is an odd degree. So if it's an odd number, then it will be an odd degree. If it's an even number, then it will be an even degree. So for example, this one, what will be the degree of this? So we have 1 edge, 2 edge, and this is technically just considered 1 edge. So 3 again. So this will also be 3. This one, we only have 1 and 2, so 2 edges. So that's how you would denote the degree of a vertex. Okay. So now we'll have a look at the faces of a network. So the faces are just the regions connecting between connected vertices and edges. So for example, this entire thing over here, so this triangle would be considered a face. And the number of faces in this diagram, for example, so just looking inside would be 1 here, 2, 3, 4, 5, 6, 7, and then 8. And then we also consider the region outside. So for example, this is the region outside, a face in itself. So that would be 9 faces in total. So very straightforward. We're just counting the number of regions that are, sort of chunked off by the vertices and edges. Okay, next we're going to be looking at the features of different types of networks. So a simple graph, so this is an example of a simple graph, it contains no loops and no multiple edges. So multiple edges just means, for example, we have 2 vertices being connected like this. So this would be considered a multiple edge because we're having vertex 2 and vertex 3 connected by this edge and this edge. So that would be a multiple edge. So a simple graph will have no multiple edges, no loops, and the sum of the degrees of all the vertices are always going to be 0. Not always going to be 0, are always going to be even. So for example, this one, we have 2, 2, 3, 2, and 2, and 3. So that will be 12. Regardless of if they're odd or even, they're always going to, in total, add up to an even number if it is a simple graph. Next, we have a degenerate graph. So a degenerate graph is one where you just have isolated vertexes, no edges. And all the vertices are therefore going to have a degree of 0, and the graph will also the graph will just have one face. Okay, so next we have an example of a connected graph. So a connected graph is essentially where there is a path between all the vertices. And what that essentially means is we have no isolated vertexes. And the number of edges that are required for any graph to be a connected graph, so we can have multiple edges. So we might have this, that will still be considered a connected graph, but all the vertices in the graph need to be connected to the network or to the other vertices in the network. So in order to work out the minimum number of edges required, that would just be n minus 1, where n represents the number of vertexes. If we have 2 different graphs almost, and they're connected by a particular line, So for example here, that would be called a bridge. This term doesn't really appear that often on the exam, so don't really stress about that one. Next, we have a complete graph. So a complete graph is a type of connected graph, but a graph in which each vertex is connected directly by an edge to every other vertex in the graph. So all vertices must be connected to all other vertices in the network. So this vertex here must be connected by an edge to this vertex, and this vertex. And to calculate the number of edges that are required, you will use this formula. So edges is equal to n minus 1 over 2, where n represents the number of vertices. So pretty straightforward. Then we have a subgraph. So sometimes we might not need an entire graph to do a particular type of analysis. We might just need a type of that graph. So a subgraph is essentially a part of that graph. So right now it's not that clear, but when we start putting actual information on the network, then it will make a lot more sense. But essentially this over here is the subgraph. So this over here is a subgraph of this entire graph over here. So very straightforward again. Next we have isomorphic graphs. So isomorphic graphs are just two different networks that represents this exact same information. So they have the exact same vertices, exact same edges, and the vertices have the same degree as well. So if we were to represent this network in a different way for whatever reason, that would be an isomorphic graph. So these types of questions appear really often on the multiple choice section. So again, just to sort of summarize, an isomorphic graph is the exact same network, just represented in a different way. So they represent the exact same information. Okay. Next, we're going to be looking at, what was that? So next we're going to be looking at planar graphs. So planar graphs are essentially a type of graph in which no two edges can intersect. So for example, in this graph, so these two graphs are again isomorphic, but in this one we have these edges crossing. So if we were to draw an isomorphic graph, so if we were to draw an isomorphic graph of this one to make sure it's planar, we need to make sure that we draw the edge with no intersecting. So we can just draw the exact same edge, just in a different way. And if we were to count the number of faces that a network have, we need to make sure that a graph is planar. So that means there's no intersecting edges. So for example, in this graph, this is not 1, 2, 3 faces. This is, we can't actually use this graph, so this one, to calculate the number of faces. We'll have to convert it into this isomorphic graph where we can clearly see the, the edges, and they're not intersecting. So therefore, it's 1, 2 faces only. So really important to make sure that the graph is, that you don't have any intersecting edges if you want to count the number of faces. Okay. Okay, so next we're going to be looking at walks, trails, cycles, and circuits, because a lot of the time, networks can be considered as as sort of like maps, almost, to represent the relationships between different sort of locations on a map. So first of all, we'll be looking at trails. So trails might just be a route that you might take where you're not repeating any edges and you're visiting vertices more than once, or you can visit vertices more than once. So for example, an example of a trail in this example would be A, B, D, C, E, B. So this is an example of a trail. We're not repeating any of the edges, but we are allowed to repeat vertices. So we repeated B 2 times. So that's the important thing, no repeated edges, but the vertices can be visited more than once. Next, we have paths. So a path is one in which you don't repeat any edges and you don't repeat any vertices. So for example, A, B, E, C, D. So you're not repeating any edges and you're not repeating any vertices. And for a path, you don't actually have to visit all of the vertices. Like A, C is a path as well, or A, B, or A, C, E is also a path. So just because some people get confused between a path and something that we're going to be learning later on. Next, we come to circuits. So a circuit is essentially where you're not repeating any edges, so you're not passing through the same edge more than once, but you can repeat vertices, and you're going to start and finish at the same vertex. So an example of a circuit might be A, B, E, C, A. So that is an example of a circuit. Remember, you don't have to visit every single vertex. So a circuit is essentially, therefore, just an example of a path. So just a path in which you're not repeating any of the edges or the vertices. But you can repeat vertices. Sorry, therefore it would be an example of a trail. So you're not repeating any edges, but you can repeat vertices. But you need to start and end at the same vertex. And lastly, we have cycles. So cycles are essentially where you are going around the map, but you're not repeating any edges, you're not passing through the same edge more than once, and you're not repeating any vertex. You're not going to the same location more than once, except for when you are at the start and the finish. So a cycle must also start and finish at the same vertex, similar to a circuit. But here, the only difference is that you can't repeat any vertices and you can't repeat any edges. So here is just a sort of an example, sort of like a summary table, which you can put in your summary book. So it's really helpful. It gives you the sort of requirements for each of these types of travel terms. Okay, so now we'll be looking at specific types of paths and specific types of cycles and specific types of trails and specific types of circuits. So the two types of paths, the type of path that you will look at is called a Hamiltonian path. So a Hamiltonian path is essentially a path, but there are specific requirements. So here you must pass through every vertex. So you need to pass through every vertex exactly once. So you're not passing through any vertex more than once. You need to pass through it exactly once. And it's a walk. And essentially, you can't repeat any edges. You can't repeat any edges, and you need to pass through every vertex more than once. Sorry, not more than once, only once. A Hamiltonian cycle, however, is a type of cycle where we are visiting each vertex exactly once. So this is just an example of a Hamiltonian path. But here we are visiting exactly every vertex exactly once, and we must start and end at the same vertex. So here is an example of a Hamiltonian cycle. So A, C, D, B, E, A. So we're not repeating any edges. We don't need to pass through all edges. That's another requirement. We don't need to pass through all edges. We just need to pass through every vertex exactly once. Next, we have an Eulerian trail. So an Eulerian trail is essentially when each edge now, so not vertex, each edge is visited exactly once. Vertices can be visited more than once, so that's not a requirement. They can be visited more than once, and they will only exist in networks with vertices that have all even except two odd vertices. So we need at least two odd vertices. Not at least, but we need exactly two odd vertices in the matrix. So for example, in this one, vertex, which one is odd? So we have vertex C and vertex B. They're both odd. So 1, 2, 3, 4, 5. Yeah, so they're both odd. 1, 2, 3, 4, 5, and 3. So they're both odd here. So therefore, this will be an Eulerian trail. So all even except two odd vertices. So we need to visit every edge, and we can repeat vertices, but we don't have to. And the way that you sort of go about formulating an Eulerian trail is you start off with the vertex that is odd, and you end up with the other vertex that is odd. Because remember, there's only going to be 2 odd vertices, the rest must be even. So therefore you will start with the one odd vertex and you will end up with the other odd vertex. So here's an example. So B, and then loop B, and then D, and then C, and then E, and then B, and then A, and then again C. So you start off with one odd vertex and you end at the other, but you must pass through every edge exactly once. An Eulerian circuit is just an Eulerian trail, but here you again must pass through every edge exactly once. The only other requirement is that you must start and end at the same vertex. So in this case, an Eulerian circuit will only exist if every edge is even. Sorry, not every edge, but every vertex is even. So if every vertex is even, then an Eulerian circuit can exist. So these are sort of the questions that you're going to get in the exam. They'll ask you, what is the requirement for an Eulerian circuit to exist, or whether an Eulerian circuit exists for this example. And sometimes they'll ask you to, give the sequence of vertices that give the Eulerian circuit, or whatever example. Next, we're going to be looking at weighted graphs. So weighted graphs are essentially a graph. So it's essentially a network where each edge is actually assigned a weight or a value. And the weight can represent a lot of different things. So it might represent distance, it might represent time, a lot of different possibilities. Most of the time it's going to be distance. So next we'll look at trees. So we will look at spanning trees. So spanning trees are essentially trees where all the vertices in the network are connected. So just a type of connected graph. A minimal spanning tree, on the other hand, however, is you'll only be forming minimal spanning trees if you have a weighted graph. So what will happen is you will use Prim's algorithm. So I'll go through Prim's algorithm. And by using Prim's algorithm, you're going to find the sort of minimal spanning tree, or the edges that have the minimum weight overall. And the way that you sort of use Prim's algorithm is you pick any vertex. So for example, might pick this one, and you draw the edge that is of minimum weight stemming from that vertex. So for example, this one's 4, this one's 6, and then this one's 3. So I will draw a line over here, 3. And then from that vertex, you will draw a line to the next edge that has the lowest weight. So it's this one over here. That's a 1 here. And then from there, you do the exact same. So you won't go back this way because you just went through that. So therefore, you might go to here. So to 2. And then you might stop there. Then you might choose another vertex. So this one over here. So essentially what a minimal spanning tree will do is it will connect all vertices, but it will be the minimum sort of weight. So overall, if you add the numbers together, it should be the minimum weight. So the Prim's algorithm basically works is you pick a vertex and then you draw an edge to another vertex from the one that's the minimum sort of weight. So for example, if you pick this vertex, it will be this vertex over here. Then you might pick another vertex, it will be this one over here. Then you might pick another one, it will be this one over here. And essentially you will get at a point where all the vertices are connected. And it's the minimum weight. Okay, so next we'll be looking at network flow. So network flow is essentially a type of question that you're going to get to in the exam, where we'll be looking at a type of flow of something. So it might be, for example, the flow of water, or sometimes you might get the flow of people, or the flow of certain items or certain things. And the way that so it's a directed graph, and the way that it sort of works is you have a source and you have a sink. So the source is where the supplies come from. So for example, if you think about for example, a plumbing system, it might be, a source of water under your house map. And the sink might be where you want the water to come, where you will be using it. And it must flow through all these pipes. And these numbers indicate the maximum capacity of each pipe, each second usually, or each for a certain time period. So this 180 might say that 100 might sort of mean that 180 liters of water are passing through this edge every second. So that's what it might sort of mean. And the way they sort of interpret this is if 180 liters of water every second are passing through from A to C, but only 90 liters can pass from C to F every second, where is this rest of the water going to go? Because only 90 liters can pass through this point every second. And then from there, only 70 can pass through this pipe. So this is a way of calculating the maximum flow. So that's what you'll be using these types of graphs to calculate. So maximum flow is overall what is the maximum flow of water that we can get each second. And the sort of requirements are it must be less than the total of the pipes leading from the source. So it must be less than the addition of 180 plus 40 plus 210. So just as a requirement if you want to check your answer. And it must be less than this amount as well. So it must be less than, this amount. So 70 plus 140. So the total flow must be less than 210, the maximum flow. And we'll be looking at how to calculate maximum flow. The way that VCA likes to sort of do this is by using cuts. So we'll make specific cuts, and I'll show you what a cut is in a second. So this is a cut. So it's sort of a line going from the top, all the way from the top to the bottom. It can't be like this. It can't be a loop like this. It has to go all the way from the top and all the way to the bottom. So for example, I've drawn two cuts here. So there'll be a variety of different ways that you can draw a cut through this graph. And what this cut is essentially going to do is it's going to block the flow from the source to the sink. And then that way you can determine what's going to be the maximum flow. So for example, and if we draw this cut over here, what you will need to do is you will need to calculate the capacity of each cut. And the way that you calculate the capacity of each cut is you look at the you add up the but capacities of each of the pipes that are going from source to sink. So you will add the capacity of this line, then you would add the capacity of this line, all the lines that it passes through, and then you will add the capacity of this edge. So after you add the capacity, it's 300. And essentially the maximum flow is the capacity of the minimum cut. So you will do a variety of different cuts to find the minimum flow. So this red one over here has a capacity of 300. It might be the minimum flow or it might not. But we've sort of already established that it can't be the maximum flow because it has to be, so if only 210 liters per second can actually go into the sink at any time, how can the maximum capacity be 300? How can 300 go to the sink at any one time? So it has to be less than 210, but we don't actually know. We can do a variety of different cuts. So we can do this one, we can do this one, a lot of different cuts. So just to give you an example, so we might do this cut, we might do this cut, we might do this cut. And the important thing to note is you're only going to add up the pipes that are going through this cut, so that are intersecting with the cut, and that are flowing in the direction towards the sink, not towards the direction of the source. So if we had a pipe, for example, like this, so if we had it flowing in this direction, you wouldn't add up the capacity of that pipe when you're calculating the flow of that cut. So really important to note. So if we draw a cut here, that's actually 210. And if you do a lot of different, so this is again a bit of trial and error. If you do a lot of different cuts, this cut would have the minimum capacity. So therefore this 210 is the maximum flow. And there'll usually be units associated with that as well. Okay, so next we'll move on to the Hungarian algorithm and bipartite graphs. So a bipartite graph is another type of network diagram, and usually what it's used to represent is a sort of relationship between different sort of vertices, or not usually vertices, but different types of... okay, so just to sort of give you a bit of an overview is a bipartite graph is used for allocation problems. And what allocation problems essentially are is, for example, if we have a project coming up and we have 5 people that are willing to, work on that project. And there's 5 different tasks that need to be performed. And each different person can perform that task in a different time or in a different overall time. So essentially, what you would need to sort of work out is what would be the best allocation such that we complete the project in the minimum amount of time. And that is what the bipartite graph can be used for. So these are very simple bipartite graphs. So for example, what this bipartite indicates is that person A can perform task W only, whereas person B can perform task W, X, Y, and Z. He or she can perform all the tasks. Person C can only perform tasks W and task Z, whereas person D can only perform tasks W and task Y. So if I was the person responsible for doing the allocations, what I would need to see is if person A can only do task W, then they must be allocated to task W, because otherwise we have one person just doing nothing, right? So that's obviously going to be a waste of time. So therefore, this would be the allocation for A. Then if we were to look at B, so B can do all of the tasks, but task X can only be done by person B. So therefore, we must allocate person B to task X, because he or she are the only one that can do it. So sometimes it's a matter of if they can do the task or not. Sometimes it's a matter of who can do it the fastest. And we'll have a look at that when we look at the Hungarian algorithm. Okay, so what about task C? So task C can only be done by... so task C can actually be done by... so person C actually can do both task W and task Z. However, task Z can only be done by person B and person C. Person B has already been allocated, so therefore, task C must be done by person Z. And therefore, the last one, task Y, must be done by person D. So that is how we would sort of work through this network. Okay. So now we'll be looking at the Hungarian algorithm. So the Hungarian algorithm is usually when we'll be looking at, So Hungarian algorithm has 7 steps involved. And why do we use the Hungarian algorithm is because sometimes we have a certain time associated with a certain task. So for example, in this table over here, we have 4 people that are working on a project, and the project has 4 tasks, and the time taken by each person in minutes is listed here. So Wendy can do task A in 30 minutes, whereas she can do task B in 40 minutes, task C in 50 minutes, and task D in 60 minutes. And we'll use the Hungarian algorithm to sort of work out the optimal allocation. So first step of the Hungarian algorithm is for each row is to work out which number is the lowest. So for example, in the first row, the lowest number is 30. So you would subtract all the numbers in the row by a 30. Similarly, for the second row, it's also 30. So you would subtract all the numbers in the second row by 30, and so on. So once we've done that, we will get this as the new table. So here we will use tables to actually do, or matrices sometimes are really useful as well. So matrix subtraction, matrix addition is going to be really useful if you can convert this table into a matrix and then use that matrix to do calculations on your calculator. Next step is to subtract the value, So next step, step 2, is to put the minimum number of lines required to cover all the zeros. So we can draw the lines in various different ways, but you have to draw the minimum number of lines to cover all the zeros. So for example, instead of these lines, what if we draw it like this? 0, 0, 0, and 0. So this won't be the minimum number of lines because we can actually cover 2 zeros by drawing just one line. So therefore, you have to find the minimum number of lines. And once you've done that, what you need to do next is, okay, so once you've done the lines, if the lines are less than 4, so in this example, since we only have 4 people and 4 tasks, the total number of lines needs to be 4 at the end of the Hungarian algorithm. But if they're less than 4, or if we have 5 tasks, and if they're less than 5, then we continue with steps 3. But if it is, then you can continue to step 6. And we'll get to step 6 soon. So step 3 is to find out the minimum number in each column. So once you've done that, so I think only in row C, the minimum number is 10. The rest is just 0. So we can just subtract 10 from the numbers in each column. Then again, you would form the minimum number of lines. In this case, you're going to get 3 lines again. So since it's not, since it's such a really low number, again, you would need to, So since it's not 4 lines, you would again need to work through the process. So the next step is to find the smallest uncovered value in the matrix. In the table. So in this case, it's 10. And what you would do is you would subtract this number from all the uncovered numbers. Now I know there might be some confusion because what if you drew the lines a little bit differently? Doesn't matter. Like whatever your uncovered numbers are, like it will work the exact same way. So whatever your uncovered numbers are, you subtract the value of this number from all your uncovered values. So for example, in this one, it's 10. So you would subtract 10 from all these numbers. And then once you've done that, the next step is to add this value to where the lines intersect. So wherever the lines are intersecting, so remember this point and this point, you would add that value. So you would add 10 to that value. And then we get this matrix at the end. So now if you draw the minimum of lines, it will have to be 4. Like this. So now you're essentially done with the Hungarian algorithm. And now it's all about the allocation. And I'll show you how from this you can go to the allocation. So what the zeros actually indicate is that Wendy can perform tasks A, B, and C in the minimum amount of time. So from there, it would be really great if you could, do a bipartite graph. It would be really helpful in certain situations. So Wendy can do tasks A, B, and C in the minimum amount of time. If we look at Xenophon, then he can do task B and C in the minimum amount of time. So we can draw a line there in the bipartite graph. Yolanda can do task D in the minimum amount of time. So there's just a line between Yolanda and D. And then Zelda can only do task A in the minimum amount of time. So now we can perform the allocation using the steps that I've shown above. So therefore, Zelda, who can only do task A, must be allocated to task A. And that will be 20 minutes. So you also look at the time from the original table of how much it's going to take. Because most of the times, the question is going to ask you to work out the minimum amount of time to complete the project. Next step is to calculate, so Yolanda, who can only do task D, will be allocated to task D, so 30 minutes. Well, not that it can only do task D, but it can do task D in the minimum amount of time. Wendy can either do task B or task C, and then Xenophon can either do task B or task C. So it doesn't really matter who you allocate to what for Wendy and Xenophon. Most of the time, this is not going to be the case. It's going to be really, really specific. So it doesn't really matter because either way, you're going to get the same answer. It's up to you which one you choose. And therefore, if we add that up together, the minimum time is going to be 130 minutes. So that's how you would use a Hungarian algorithm to work out the minimum the best allocation. Okay, so now we'll be moving on to activity networks. So activity networks are usually when you have some form of project and there's a lot of different tasks or activities involved in completion in order to complete the project. But the thing is, when we're doing a really large project, certain activities or certain tasks need to be done before you can commence a different task. And that's what a predecessor is called in an activity network. So for example, if we're starting at this point and we're ending at this point, the first activities that we need to do are activity A and activity B. And then before we can start activity C, we need to have done activity B. So this is how we sort of read that activity network. And the numbers next to the A show the approximate sort of time that it's going to take to do those activities. So if activity A is going to take 2 minutes or 2 hours, depending on the question, activity B is going to take 4 hours. So if we were to draw, so this is called the precedence table. So in order to write up the precedence table, all we need to do is write down all the activities in the project and then just write the immediate predecessors. So the immediate predecessors are just the activities that must be done immediately before. So for example, for activity D, the immediate predecessor is activity A. So the activity that must be done immediately before it. And so on. So here is the immediate predecessors and also the time. So this is the precedence table. But a problem that you will shortly know when you write up the precedence table is the fact that some activities, for example here, might have one of the same predecessors, but not all immediate predecessors are the same. So for example, activity D has an immediate predecessor of activity B. But activity E has immediate predecessors activity B and activity C. So that's a little bit of a problem because when we're drawing the activity network, when we're drawing up activity E, if we draw the line going from activity B all the way to activity E, and then we draw activity D as well, that will show that activity C and activity B are the immediate predecessors of activity B. But that's not really the case. It's only activity B. So we draw a dummy activity. So a dummy activity is where multiple activities share one but not all immediate predecessors. And by drawing up that dummy activity, essentially what we're doing is, so if we draw a dummy activity here, essentially what we're showing is activity D has an immediate predecessor of activity B. But activity E has an immediate predecessor of activity C and also activity D, and also activity B. So that's what it's used to sort of show. Dummy activities have a time of 0. They don't take any time. It's just there to sort of make sure the activity network is correct. Okay, so some quick definitions before we go on to critical path analysis. So a critical path is essentially the path through a network that takes the longest amount of time. And all other activities sort of work around it. And then we have earlier starting time and later starting time. So the earliest starting time for any activity is the earliest time at which that activity can be started. And then the latest time is essentially the latest time that an activity can be started without affecting the critical path. So the goal of critical analysis is not to affect the critical path, because if we affect the critical path, then we are essentially going to increase the amount of time that it takes to finish off the activity. The project. And the float/slack time is just the amount of time that a particular activity can be postponed without affecting the critical path. And the way that we find the float or slack time is essentially by subtracting the earliest starting time from the latest starting time. Okay, so now we'll have a look at doing forward scanning. So forward scanning is a really important skill when we're doing critical analysis. And the way that we do forward scanning is essentially just finding the earliest starting time for each activity. So for example, activity A, it can be, the earliest starting time is 0, so it can be started at any time. However, activity C must be started after 8 hours or after 8 minutes Because activity A must be started before starting activity C. So that's why the earliest starting time for activity C is 8. And then for activity E, it is 9. Because activity A and activity C must be done before starting activity E. Similarly for activity, okay, so then we'll move on to this path. So for this path, the the early starting time for activity B is 0 because it can be started at any time because we don't have any immediate predecessors. Activity D, however, must be started after 6 hours because it needs to, because activity B must have been completed before starting activity D. Activity F is a little bit weird. Both activity A, activity C, activity B, and activity D need to have been completed before starting activity F. However, if activity A and activity C take 9 hours to complete, and activity B and activity D take 8 hours to complete, this is sort of like the critical path. So activities A and activity C must have been done before starting activity F because these take 8 hours, whereas these activities take 9 hours. So the minimum starting time or the earliest starting time is 9 hours. And then for activity G, so if we look at activity G, if we look through this path, it's activity A, C, and E must be done before starting G. But if we look at this path, activity A, activity C, activity F must be done. So which one's the longest? So activity H, A, C, and E is, what is that? That's 12 hours, where activity A, activity C, and activity F is 10 hours only. So therefore the earliest starting time is 12 hours. And then H is just going to be 14 hours because activity G, which is 2 hours, must be completed before starting activity H. And then essentially we find the earliest starting time. So 15 hours is the time that's going to take to complete the project. So next step is to do backwards scanning. So backwards scanning is just the exact opposite. So we start from the finish line or the finish of the project, and then we move. So essentially we find the latest starting time that it can start. So 15 hours, so 14 hours. So it needs to be started 14 hours. So it needs to be started after 14 hours, and that's the latest starting time. However, activity G, so we subtract 2, 12 hours. Activity E, so you go backwards like this. So this would be 9, because 12 hours minus 3, which is 9. And activity F would be 12 minus 1, which is 11. So see how it's a little bit different, the numbers? Because here we were going like this, and here we're just going like this. So 12 minus 1 is 11. And then F minus D is, so 11 minus 2 is 9. And then 2 minus 3, 6 is, sorry, not, so 9 minus 3 is, 9 minus 6 is 3. So those are the latest starting times for this path. So if we look at this path, however, we have 9 minus 1, which is 8. So for example, for C, we have 2 parts going in. So we have E and we also have F. So out of F or C, you choose the one which has the lowest latest starting time. So since E has the lowest latest starting time, you will use this to work out the latest starting time for activity C. It's just a little bit of a problem that some students might get into. Okay, so therefore this will be 8, and then if we subtract 8, it will be 0. So that's essentially critical path analysis. And then the actual critical path is the one in which the latest starting time and the earliest starting time are the same. Essentially, the path where we have no float time, whereas all of these are going to have float time. So these activities are not critical, whereas all of these activities are critical. Okay, and now we move on to crashing. So crashing is just involving the chain. So sometimes we might need to change the conditions of the activity in order to reduce the completion time. So this might include reducing the individual times it might take to complete activities on the critical path, or sometimes it might be changing the activity times of different activities, and therefore that's sort of changing the entire sort of critical path. So there's a lot of trial and error, and you will, and this is best done by doing a lot of practice questions. And then another thing that you will be having a look at is crashing with cost. So crashing with cost is sometimes when a certain cost is associated with crashing a particular activity. So crashing is essentially just reducing the time that it takes to for an activity to sort of occur, or the time it takes for it to complete an activity. So if activity D, for example, takes $150 per hour to reduce, and activity E takes $180 per hour to reduce, and they're both on the critical path, it will be much more beneficial to reduce the cost of activity D because that only costs $150. So that's just crashing. So crashing with cost is just when you reduce the time, but there's a certain cost associated. Okay, and lastly, so thank you everyone for joining in to today's lecture. I just want to go through some exam tips. And if you have any questions, let me know as well. I'll be monitoring the chat. So my main exam tips for general maths is doing lots and lots of practice exam questions, starting really early. Starting now would be really, really beneficial. So even if you're not doing the entire exam, maybe just doing the data and the financial section, if you've completed those, that would be really beneficial. So you don't have to cram at the end of the year. Also being consistent. If you're not doing, I'm not asking you to do like 5 practice exams starting now every week. But even if you do like 1 per week, or 1 or 2 every 1 or 2 weeks, that's like really good, because a lot of people are just going to start when it gets to the exam season, and at that time it's going to be really sort of inefficient, I would say, because you have a lot to do, and general maths is just a subject that requires a lot of practice questions, and a lot of practice to get really good and perfect at. Also, finishing off your summary book as early as you can. So these holidays are a really great time to finish. To finish off your summary book, or finish off most of your summary book. And every exam that you do, add the difficult questions from the practice exams. So summary book is not just for notes; it's also for difficult questions from the practice exams that you have done. And lastly, ask your teacher for help when you need it. So teachers are there to help you, and you can also ask them for free resources. And if you need any other resources, remember to check out the HR Notes resources, as well as the Tutor Smart and Ed Unlimited service. Thank you everyone for joining in today, and good luck for the end of your exam.